So this is going to be a guide going over a thermodynamic heat exchanger problem. This is a steady flow problem where there's some exchange of heat. You can see here we have hot water flowing through cold water to heat up the cold water and or cool the hot water. So we have cold water leading into a shower, enters a thin double-walled pipe counterflow heat exchanger at 15 degrees Celsius at zero point 0.6 kilograms per second and is heated to 45 degrees Celsius by hot water that enters at 100 degrees Celsius at a rate of 3 kilograms per second. So determine the rate of heat transfer in the heat exchanger and the exit temperature of the hot water. So first thing you're going to want to do in a problem like this is always draw it out so you know what's going on. You can see here we have the hot water with a flow rate 3 kilograms per second entering at 100 degrees Celsius, and we're trying to find out what temperature it leaves at. Then we have the cold water here, same flow rate of 0.6 in and out, and there's going to be some heat flow, Q, going from the hot water to the cold water, and that's what we're going to try and find first. So right here, we're finding Q, the heat transfer rate. We're going to start by setting up a balanced equation here. We have the mass flow rate times the specific heat times enthalpy going in equal to the mass flow rate, specific heat, enthalpy going out. The only difference is when it's going in, it's going to have that additional Q, that heat transfer, that's coming from the hot water. And then we can rearrange this so we get Q, heat transfer, equals mass flow rate 2 times specific heat, enthalpy 2 minus the first mass flow rate, specific heat, times the first enthalpy. We can plug these numbers in. So we get 0.6 kilograms per second because both the flow rates are the same. This is steady flow, it's not changing. That times 4.18, the specific heat, kilojoules per kilogram. And that whole thing is being multiplied by the difference in enthalpy, or the enthalpy at state 2 minus the enthalpy at state 1. So we're going to simplify the first part. Q equals 2.508 kilojoules per second times, and then this change in enthalpy is equal to the change in temperature. So T2 minus T1, which we know. So then we get 45 degrees Celsius minus 15 degrees Celsius for the difference in temperature, and a final heat transfer rate of 75.24 kilojoules per second. So in the second part of this, what we're trying to find here is the exit temperature of the hot water. We know it enters at 15 degrees Celsius, loses heat to the cold water, and we don't know what temperature it leaves at. So we're going to set up a balanced equation here, similar to the last one, except this time it's for the hot water. So we have Q out, or the heat that's leaving the system, plus the mass flow rate, specific heat and temperature at state 1, equal to the mass flow rate, specific heat and temperature at state 2, plus Q in. We know that that's 0 though, so we can just kind of ignore that. Then we have rearranged this. Q out equals specific heat times mass flow rate. We know this is the same for both. It's steady flow going in at 0.6, going in at 3, leaving at 3, times the difference in temperature. So plug in. We know 75 kilojoules per second are leaving the system. 4.19 kilojoules per kilogram times the mass flow rate of 3 kilograms per second times T2 minus 100 degrees Celsius, which is T1. So then flipping the T to the other side, we get 12.57 kilojoules per second times T2 is equal to 1,181.76 kilojoules per second. And then finally, divide this out, we get T2 is 94.014 degrees Celsius. And that's all for this problem.